Okay, we're going to continue on here, chapter 9, I think. And we've been talking about solutions. And last time we talked about some ways to classify solutions. Again, a reminder, solutions are the things that have the aqueous symbol. Again, there are two components to a solution, a solute and a solvent. And remember that a solution really is a homogeneous mixture, which means everything mixes and it all should look like one sort of substance. The solute, again, is the smaller part of the solution. The solvent is the larger part of the solution. And one of the things we talked about last time was also sort of solubility. And the idea, as we talked about, of like dissolves like. So, again, things that use very similar forces like intermolecular forces that they use with themselves will typically mix and work really well with others that use the same type of forces. All ways that pretty much molecules interact with each other, as we talked about last time, is through a very simple kind of opposite attraction between the two different molecules. And that is basically the positive side of one molecule is attracted to the negative side of the other. And those are basically what intermolecular forces, all of them pretty much are. There are some that are stronger intermolecular forces than others, like hydrogen bonding is the strongest, dipole is pretty strong, and also dispersion forces is the weakest of them all. But in terms of things being able to mix really well with each other, they pretty much need to interact with whatever they're mixing with the same way that they pretty much interact with themselves. And that makes things really mix really well. So as we talked about, there's sort of a list of things that are soluble. And again, that is your ionic and your polar and polar things, and your non-polar and non-polar things. These guys should really have no issues when they're mixing together. And again, that is because they're using the exact same forces that they use with themselves. So it's pretty natural for them to be able to interact the same way as they interact with themselves. Again, we only kind of get that little difference as we talked about as we sort of cross over polar and non-polar. What the main problem is when we try to do those two things is they are using very, very different types of forces. And the polar molecule is always good to go to interact. It's always got a positive side and a negative side. The problem really is the non-polar molecule. It doesn't have a positive side or negative side. It needs something to happen to temporarily create that for it. And that's why it can only sort of interact for a short period of time. And it won't be able to maintain those interactions. We talked about how we know in terms of when we take a positive ion and a negative ion and make an ionic compound, will it be soluble or insoluble? Basically, we'll get the aqueous or the solid symbol. And those were our solubility rules that we went through. And remember that we could use solubility rules to help us decide when we put two ions together to make an ionic compound, would we expect that basically to be a solid, which essentially will mean that it will fall out of solution. It's really not going to be floating around in a sense, or if it's going to be soluble, which means they're going to basically mix and not really stay together, and all the ions are just going to be basically floating around in the solution part. There are certain things that no matter what you put with them, they're going to be soluble in everything. So things in group one, things that have nitrate, things that have ammonium, they are soluble in everything. So if you see any of those things in an actual chemical formula for an ionic compound, you should think that it should be a solution. It should be soluble. There are certain things that are still soluble, like chlorides, bromides, and iodides in most things. But there are three exceptions, like we saw in a couple of our examples: silver, lead, and mercury. So if you have any of those guys that hooked up with something like chloride, for example, it wouldn't be insoluble. So those solubility rules, as we talked about, you do need to be able to use them correctly. They probably, again, will be provided for you if you need them, but you just have to kind of use them. Remember, if it is insoluble, that is the symbol that it should get, really. That's going to be solid. And if it's soluble, that is the aqueous symbol that it should get. We then talked about some other things. We talked about electrolytes, and there are strong, weak, and non-electrolytes. And remember that if it is a strong electrolyte, that means that essentially it's going to 100% break apart into ions. So you will have nothing that stays together as like the whole unit. You basically will just have a bunch of ions floating around that solution. And that's really important because electrolytes are things that can conduct electricity. And it's really the presence of those ions in the solution that allows it to conduct electricity. So when you have a strong electrolyte, you just dumped a bunch of ions floating around in that solution. And that means that if you wanted to conduct electricity, it will go off really, really strongly. And again, the light bulb example that we talked about, again, it would be very, very bright light bulb that would go off as it's conducting electricity really, really well. A weak electrolyte, on the other hand, is something that actually mainly stays together, but does break apart a little bit. And because it's still able to break apart a little bit, it will still be able to produce a little bit of ions floating around that solution. And those little bit of ions are crucial for the fact that it can still conduct electricity. It will not be able to conduct electricity anywhere near a strong electrolyte. But because there's still a little bit of those ions in solution, it will still be able to conduct electricity. So again, if we use sort of our light bulb example, it's going to be kind of a dim light bulb. It will still be able to kind of turn on, but not very, very brightly. One of the main distinctions in terms of the equations that you can tell between them is a strong electrolyte has a one-way arrow. Everybody's just dumping out to the product side, creating all those ions. Weak electrolytes are reversible reactions, which typically have the arrows that are heading in both directions. The non-electrolyte is something, again, that will dissolve in water, but the difference is it will not create any ions. And even though it's able to dissolve in water, because it does not have any ions that are created, it will not conduct electricity. So I think we talked about sugar as an example of that. Sugar, again, is carbons, hydrogens, and oxygens. Those are all covalently bonded together, sharing electrons, no ions. So even though it will dissolve, it will not create any of those ions. It will not conduct electricity. So again, in an equation, how you sort of recognize that is those guys also will probably have a one-way arrow. You'll kind of have like the same thing on both sides, but no ions formed on the right-hand side. So there will be no ions in the right-hand side of the equation. Then we talked about equivalence, I believe. And equivalence, for the most part, the way we will use it is in the term of a very common sort of unit for solutions, which is equivalence per liter, or whatever I was going to say there, or milli equivalents per liter. I'll spit that out. And you could kind of think of this as sort of a concentration unit that is sort of based on the charge. And that's sort of how we get the equivalence for the ions that are present in the solution. And it is all based off of the charge. So if you have a sodium ion, and it's really not the positive or negative part of the charge, it's actually the number that's most important when you're kind of doing this. And because that's a 1, we could say for every 1 mole of sodium ions, we get 1 equivalent. It doesn't matter if it's positive or negative, the charge, but once again, it's really just a number. So if we had sulfate, like we had an example, 1 mole of sulfate will give us 2 equivalents. So what we did see when we did a couple of examples was when you have an ionic compound, and the way that we sort of put together an ionic compound properly is to balance out all the positive charges, right, with the negative charges. So in terms of this type of concentration, what ends up happening is if you figure out the equivalence per liter for each of the ions in a solution, like the positive guy and the negative guy, they actually should come out with the same number. And that is because the overall charge of those ions are balanced in that solution. And that's why, for example, I think we did sodium sulfate, I think, is one of the examples. You need twice as much sodium ions floating around there because each sodium only has a +1 charge to balance out the -2 charge that's in that solution for the sulfate. So in terms of this sort of concentration, what you actually end up getting for both the positive and the negative ions should always really be the same sort of equivalence per liter, because the charge should be balanced if it's a proper ionic compound. We finished up on, I think, talking about one type of concentration unit, which is percent mass to mass. And this is the mass of the solute divided by the mass of the solution times 100%. And remember on this one, it really is the bottom one that's very important, because historically in these type of problems, they will give you both the solute and the solvent numbers separate from each other. And it's very common that people will just kind of divide by the solvent part. So you want to make sure that you do get both of those parts in there, the solute plus the solvent, when you do that. And again, they are typically given separate from each other. Any questions on any of that stuff we talked about last time there? All right, then let us continue on. So I think we did an example to finish up on last time. So let's take a look at another example here. Concentrated hydrochloric acid is 37.2% by mass HCl. What is the mass of HCl that's contained in 35.5 grams of the concentrated hydrochloric acid solution? So take a few moments there to see what you come up with. Looking for the mass of the HCl in this solution, and that is the mass percent of it there, 37.2. Okay, so let's take a look at this. We're dealing with here percent mass to mass, which obviously, again, our formula, our percent mass to mass is going to be our mass of our solute divided by the mass of the solution times 100%. In this particular case, we are given the percent mass to mass, which is our 37.2%. We are looking for the mass of the HCl, which is our solute. And we have the mass of the solution, which is 35.5 grams. So you may be asking, how do I know that 35.5 grams is the mass of the solution? Well, I'm asked to find the mass of the HCl in this case. Remember that when you have a solution, whatever the name of the solution is the solute. So if I'm asked to find the HCl, that would mean I'm looking for the solute in this case, and the 35.5 grams would have to be actually the mass of the solution, just in case it didn't say that. So again, the solute's always the name of the solution. And so that's how you know if you have to solve for how much of that is the solute. So you can obviously plug and chug into this equation if you like, since you do have this, and you can solve for this. You could also, again, if you maybe don't remember this equation or not sure, you could take more of a dimensional analysis approach to this calculation, where frankly, it might not even have to worry about the equation or formula. And remember that, as we talked about, when we do have something that is 37.2% in this case, what that means is we could turn this into a conversion factor of 37.2 grams of HCl in 100 grams of solution. And we could also flip it around with 100 grams of solution would be 37.2 grams of HCl. So if you want, you could kind of turn that percentage into a conversion factor. And now you really don't have to think too much about the formula. You could just get rid of the units you don't want, which is obviously the solution part. So you could do more of a dimensional analysis calculation where you take 35.5 grams of solution, opposites to cancel. And that obviously means we would want to use it just like this here, which would give us 37.2 grams of HCl and 100 grams of solution. Grams of solution will cancel. 35.5 times 37.2 divided by 100, going to give us 13.2 grams of HCl in this particular case. Now, by the way, that is the exact same math that you would do if you just rearrange the equation as well. But again, if you can't maybe remember the equation or formula there, you could take, again, a more just a get rid of units type of approach, dimensional analysis approach. Because again, if we took this equation and solve for the mass of the solute, that would be the mass of the solution times the percent mass to mass divided by 100%. And that's essentially what we just did there. There's the mass of the solution, there's the percent, and divide by 100 basically. So again, it's the same really math, but a way you could maybe get to the answer if you can't remember the actual formula or something like that. Any questions on that? Yeah. Yeah, so the idea pretty much whenever you have like a percentage of anything and you want to kind of turn it into like a usable sort of conversion factor or number, the easiest thing to do is assume you have 100 of whatever it is. And the reason you assume you have 100 is that basically keeps the percentage number and the number you're going to use the same, right? You could assume anything you want. You could assume 200 grams, but you would have to double that mass and you're doing a lot more. So when we assume 100 of it, that keeps the number the same. To answer the second part of your question, in this particular case, it would be grams over grams because it's a percentage of mass to mass. So that basically means grams over grams. And if it was a different percentage, like we'll see in just a second, it wouldn't be grams over grams. But in this particular case, because it is mass to mass, it would be grams over grams. Other questions? Okay, so let's talk about actually some other percent concentrations where it is similar but a little bit different. And the next one is percent volume to volume, and that is the volume of the solute divided by the volume of solution times 100%. So this is really, in a lot of cases, milliliters over milliliters in this case. So for example, if we had our, say, 4.5% mass to mass sodium chloride, like we were just talking about previously, we could turn that into 4.5 grams of sodium chloride in 100 grams of solution. Or again, obviously, you could flip it the other way. Now, if we have it as 4.5% volume to volume sodium chloride, when we convert this into sort of a usable unit, because it's volume to volume, we don't use grams in this case. We could do something like 4.5 liters of sodium chloride in 100 milliliters of solution. And again, we could flip that around as well and use it as a conversion factor the other way. So the percent mass to mass or percent volume to volume is important in terms of, obviously, if you turn it into a conversion factor, what units you should use. And it is based on the percentage that you're dealing with in that case. Otherwise, other than that, it's pretty much solved the same way. We got the volume of the solute divided by the volume of the solution. The good news usually in this type of problem is they just straight out give you the volume of the solution. So unlike the first one where you have to be really careful about the solute and the solvent, you don't have to be as careful in this sort of type of problem because a lot of times they'll just tell you how much volume of solution you actually have. So that's sometimes a good thing. The only kind of variation on that is they may give you a gram of solution and maybe the density, and you could use the density in the grams to get to the volume of it, the milliliters, using density formula. So that's a slight variation that occasionally may pop up, but most of the time I would say they probably just straight up give you the volume in milliliters. Now, with that, there's one more sort of percentage unit that sometimes we come across, and that is percent mass to volume. So this is basically grams over milliliters, mass over volume. So grams over milliliters is kind of like density, grams over milliliters with a percentage though. So this is the mass of the solute divided by the volume of solution. So just like the other ones, if we had a 4.5% mass to volume sodium chloride solution, what that would mean, again, if we're going to turn this into sort of a usable conversion factor, we would have 4.5, and these would be grams of sodium chloride because that is a mass over 100 milliliters of solution. So again, the sort of percentage that you have, either mass to mass, volume to volume, or mass to volume, will dictate again how you kind of convert that into a conversion factor if you were to use it in that fashion. Again, other than that, it's pretty much kind of solved the same way as the other two. And also on this one, you most of the time will just have sort of the volume of solution without having to worry too much about the solute and solvent. Again, it's possible it could be different, but most of the time they probably just have the solution. Any questions on that there? All right, so let's try one here. What is the mass to volume percent of Br2 in a solution prepared by dissolving 12 grams of Br2 in enough carbon tetrachloride to make 250 milliliters of solution? Okay, so let's take a look. We're looking for our percent mass to volume in this case. which once again is going to be our mass of our solute divided by the volume of solution times 100%. In this case, the Br2 is our solute, as it's the smaller part of the solution and being dissolved in the larger part here, which is our carbon tetrachloride, which is actually our solvent in this case. And that means we really have everything we need in the right unit. So we'll go with the 12 grams over 250 times it by 100%. And that's going to give us a 4.8%. And in this case, we really won't keep the grams or milliliters. We would just use the percentage there and specify that it is mass to volume here of a Br2 solution in this case. Yeah. Any questions on the calculation there? Why in this case are they using carbon tetrachloride as a solvent and not water? Yeah, the Br2 is nonpolar, right? So Br2, right, is this, with an R, and that is nonpolar, which means if we take carbon tetrachloride and quickly sketch it without all the dots on the outside, that is a symmetrical geometry, right? Which means it is also nonpolar. So those two guys are going to work really well together. This would be a case where water would be a terrible solvent because it's not going to do much with that Br2. They're not going to mix or anything like that. So again, remember, water is a good solvent for a lot of things, but not always the correct solvent for everything. And in this case, this would be a much better solvent. Any questions on that there? Okay. All right, so let's try one more here. Calculate the grams of KCl and the grams of water in a 225 gram of a 8% mass to mass. Okay, let's take a look. So obviously we're dealing with percent mass to mass. So we have our formula here. Again, our mass of our solute divided by our mass of our solution times 100%. In this case, we are looking for the grams of the KCl. So we're looking for the mass of the solute, which is our KCl. In this particular case, once again, I know that that's the solute because that is the name of the solution. So that is the solute in this particular case. We're also looking for the mass of the water as well that's been there. In this case, right, the water here would be our solvent, right? And KCl is an ionic compound, so water is a really good solvent for that one. It's going to work really well together. All right, and we do have the percent mass to mass given to us here, which is 8%, and we have the mass of the solution here, which is 225 grams. Once again, I'm going to take more of a dimensional analysis approach in this calculation. So I'm going to turn my percentage into really a conversion factor. You once again as well, if you would like, you can just plug into the equation. We will get here basically 8 grams of KCl over 100 grams of solution. And again, that comes from the percentage. Or we could use it in the opposite sort of direction there if we need. 8 grams of KCl. So taking the mass of my solution here, which is 225, I am going to use the conversion factor there on the left. And that's going to tell how many grams of KCl I will need in this particular case. The grams of solution will cancel, and that will get me 18 grams here of KCl. Any question on that part of the calculation? Now, to get my water, right, that will come from this guy, right? The mass of my solution is both the solute, which we just found, which is KCl, and the solvent in this case, which is the water, right? So now that we know how much of that is basically the solute, we could basically subtract and figure out how much of it is water. So the mass of the water in this case will equal our 225 grams, which is our solution, minus our 18 grams, which is our solute. And that's going to tell us about 207 grams of water was also needed, right? So basically 207 grams of water, 18 grams there of the KCl gives us a total mass of the solution of 225 grams. Any questions on that there? Any questions on percent concentrations? So not use a tremendous amount, but does pop up occasionally along the way, especially with solutions. Percent mass, percent by volume. That's what they use for like alcohol when they say alcohol by volume, right? Percent by volume. That's percentages are sometimes used with solutions. Any questions? Okay. All right. So now that we talked about these percent concentrations, once again, here's just a little table that talks about how to turn them into conversion factors, which we sort of talked about there. Let's talk about really the main sort of concentration unit and the one that's used the most with solutions. And we touched a little bit upon it the other day when we were talking about equivalent. And this is molarity. And molarity is abbreviated with a capital M. And that stands for really moles of solute per liter of solution is really the sort of titles there. Overall, though, most people just look at it as moles per liter is essentially the formula. So molarity, which is probably that most common unit of concentration, is our moles per liter. You could think of it like a formula, kind of like density, because very often we will solve for one of these three things, or all of these three things are in play. So we don't always just solve for molarity. We sometimes have the molarity and have the volume, and we need moles, or vice versa. We might have the moles of molarity and need the volume, which is the liters. So you should think of this really as sort of like a formula. And you could rearrange it the same sort of way if you wanted liters. That would be moles divided by the molarity. If you wanted moles, which is a very common calculation, you would need liters times molarity. So it's sort of like a formula that's used. And like I said, it's very common to solve for any one of these three things, given the other two sort of pieces of information. Now, if you have a molar solution, which is what molarity is sort of referred to, like if you had a 4.5 molar sodium chloride solution, what you should really do in all cases when you're using molarity in a calculation is you really should take more of a dimensional analysis approach. And the first thing that you really should do is get rid of the big M. And you should replace the big M with both of the units, and that would be 4.5 moles per liter of sodium chloride. The number always stays with the moles part, and the liter is always 1 liter. So it's always 1 liter for the bottom part, the liters part, and the number should always be with it. The reason you should, in calculations, take more of a dimensional analysis approach and get rid of the big M is because when people do not do that, most of the time, nobody has a clue about the volume part at all, like where the liters is it on top, is it on bottom? Should I divide? Should I multiply? And they usually will do it wrong. And the second most common thing is they have no clue that liters is even there. They just see the M and think moles and forget all about the volume part. So I would highly recommend when you're doing calculations, you get rid of the big M, put both of the units there so you can visually see both of the units and hopefully kind of know what you should be doing in terms of your calculations. And that's a super very common mistake that people make. It's like they just leave the big M and they have no idea about the volume. And a lot of times they're never even sure it's even there. They just think, again, moles with that. All right. So when we do have a 1 molar solution of sodium chloride, that means, again, that we have basically 1 mole of sodium chloride per liter solution. How molarity and concentration relates to ions is also sometimes really important. And so, for example, we know that if we have a sodium chloride solution, that is a strong electrolyte, which means really when we have a sodium chloride solution, that's going to 100% break apart in the solution into the ions, which means really the only things we have floating around in the solution are the ions. And sometimes we will be interested in maybe not the concentration of the whole thing together, but maybe we're interested in one of the ions that are floating around or the other ion that's floating around. So how molarity works with the whole thing versus the ions is kind of like stoichiometry and sort of how it breaks apart. So for example, if I did have a 1 molar solution of sodium chloride, what that really means in solution, I have only the sodium ions and chloride ions floating around. And if I wanted the concentration of the sodium ions by itself, it is a 1-to-1 relationship between, again, how they break apart. And that would mean that I would take 1 times our 1 molar, and that would give me 1 molar in terms of the concentration of the sodium ions that are floating around that solution. It is also a 1-to-1 relationship between the whole thing and the chloride ions. And that means that I would take 1 times the concentration of the whole thing, and that would tell me that the concentration of the chloride floating around is 1 molar. So molarity is not additive, so clearly 1 and 1 equals 2 still. But in terms of concentration, that's not how it works. It's sort of related to how it breaks apart in the solution. And it is different if you have, obviously, more than one thing. Like if you had I think we looked at a sodium sulfate the other day. And again, in this case, when this breaks apart, we will get 2 sodium ions and 1 sulfate ion, basically. I don't really need to put the 1, but I'll put it there. And again, if we had 1 molar of our sodium sulfate, it is a 1-to-2 relationship between that and the sodium ions. So in this case, it is twice as concentrated in terms of the sodium ions. So we would multiply it by 2, and that would give us 2 molar for our sodium ions. It is a 1-to-1 relationship between that and the sulfate, which means we would take 1 times our 1 molar, and that would give us 1 molar for our sulfate. So the quick way to do it is based on how it breaks apart. What we're really doing when we are doing that is a longer calculation that we're really not doing, which is a stoichiometry type calculation. So just to show you the longer version of the calculation, so you can see why we're doing 1 or 2, we'll take this guy, for example, here. And if we did this, we would have started with 1.0. And again, I'm getting rid of the big M and putting moles per liter of my sodium sulfate. And now when I do my mole to mole relationship, just like in stoichiometry, right? It is a 1 mole of the whole thing gives me 2 moles of the sodium ions. So that is what I'm going to use, like a conversion factor here, 2 moles of sodium ion and 1 mole of the whole thing. Moles of the whole thing cancel, and that leaves me 2 moles per liter of sodium ion, which is basically what I got right here. And if I did the longer version for the sulfate, and 1 mole per liter of the whole thing, and if we look at it as a 1-to-1 relationship, which means I have 1 mole of the whole thing, just like in stoichiometry, coefficient, 1 mole of the sulfate. And again, using that as a conversion factor, 1 mole of the whole thing. Moles of the whole thing cancel, leaves me with 1 mole per liter of sulfate. That is the longer version of just multiply by the coefficient, and that will come out the same. That is why on the first one here, I multiply by 2 because it is a 1-to-2 relationship. That is why here I multiply by 1 because it's a 1 relationship. So the quick way to do it is just to understand how it properly breaks apart in solution. And if it breaks apart into 3, you would multiply it by 3, right? So if you got like a 1-to-3 relationship, you would multiply the molarity by 3. So that is how the molarity of the whole thing relates to basically the molarity of each of the ions that are floating around there. It is proportion wise what you have floating around. And as we saw when we did equivalents per liter, the necessary of that is to balance out the charge, right, in the solution. So everything balances out, all the positive charge and the negative charge. So you need twice as much concentration, in this case of sodium, as you do in terms of the sulfate. Any questions on that? All right. So again, this would be a situation where you're maybe not interested in the entire thing, but just, one of the ions that may be in that solution. All right, so why don't we try an example here? We want to calculate the molarity of a solution prepared by taking 15.6 grams of KBr in enough water to make 1.25 liters. I would look at the periodic table, but apparently went down, I think. So it's over there, I think. All right, potassium is, I think, 3910 still. And our bromine is 7990. Why not? Take a look. So clear, we're going for molarity, which means we need moles per liter. So we want to think about, do we have any of that given to us already? And hopefully you see we do have the volume given to us, and it is in the correct units, which it does have to be in liters, by the way. We have the mass here of our solute, which is 15.6 grams. So we don't have the moles here, but we can go from grams to moles, and we know how to do that. That should again be the molar mass, right, from the periodic table. To do that, that's a K and a BR, which means we're essentially just going to add those two together. That's going to give us like a 119 grams per mole as our molar mass here for KBr. Remember, we're going to use that as a conversion factor to go from grams to moles. So we'll go 15.6 grams of KBr using the molar mass from the periodic table. We do want grams to cancel, so it needs to go on the bottom to do so. And that will give us 119 grams per mole of KBr. The grams here will cancel. And again, that means we're going to take 15.6 basically and divide it by 119. And that will get us 0.131 R. That is essentially now the top part that we need. What's left to do is basically just divide the two. So molarity here will take our moles. We'll divide it by our volume, which was given to us. And that was going to get us here. Looks like 0.105, it looks like. Now, in terms of the units, you can leave it one of two ways. You can leave it moles per liter of KBr. Or if you want at this point, you can get rid of the 2 units and just write big M KBr. So either way that you would want to sort of give that. Another very common sort of conversion, in addition to grams to moles, that's used a lot with molarity is milliliters to liters. Yeah, so once again, 1,000 milliliters is equal to 1 liter. So that's very, very common conversion. A lot of times the volume is given to you in milliliters. So a lot of times you do need to convert it to liter. If you are ever doing a calculation that involves molarity and volume by itself, always the liters. So volume's always got to be the liters, because that will give you what you're expecting to get, which is the moles. Any questions on that one there? So let's say we want to know how many milliliters of a solution can be made from let's go with, I don't know, we'll go make up a number, hope for the best, 125 grams of sodium chloride if we want a molarity of, let's go with 0.755 molar. I'm going to do it as well because clearly I just made it up, so we'll hope for the best here. Sodium is 22.99 and chlorine is 35.45. All right, so take a few moments. I'll do it as well. Hopefully, didn't making up numbers here. So clearly, we're doing something with molarity. So we have molarity as our moles per liter. We're looking for milliliters of solution, which basically means we do want the liters part. So eventually, we are going to rearrange this equation and solve for liters, which is moles divided by molarity. We're going to multiply the liters to both sides and come back and divide by the molarity backwards. Oops, that way. And in this case, we do need both of those things. So we definitely have the molarity given to us, which is good. We do not have the moles, but we do have the grams of the solute. So again, we can convert those into moles by using the molar mass. So that's what I'm going to do here. I'm going to start with the molar mass, which in this case is also just adding these together. So that's a 2299 plus a 3545. It's going to give us a 58.44 grams per mole as our molar mass of sodium chloride. Again, we're going to use that as a conversion factor here to get our sodium chloride into the correct units. In this case, we're going to put our grams still on the bottom and divide by them, basically. Grams will cancel. So that's a 125 divided by a 58.44. And we'll go with 2.1389 moles of sodium chloride. Now I do have the moles. I am again going to get rid of the big M as I talked about earlier and replace it here with the 2 units, and again take a more dimensional analysis approach so I do not forget how things should cancel out. So when you have that 0.755 big M, that means moles per liter of sodium chloride, and that would then be liters over 0.755 moles of sodium chloride. So again, that is basically the 2 conversion factors that you could get from the molarity. And we can now clearly see both units. And that should also help you do this correctly, just in case you do not rearrange the equation correctly. You could take this approach, and all you have to remember, like a normal dimensional analysis, is opposites cancel. So I want to desperately use the one here on the right to do that. That's going to give me liters of sodium chloride, 0.755 moles. The moles will cancel. This will also hopefully help you realize that you are not in the correct units after you do this calculation, because what units am I in right now? I am in liters, right? And I want milliliters. So again, there is benefits to getting rid of the big M and using both of those units so that you can see what units you're left with. That means I do need to go one more conversion here, right? And there is 1,000 milliliters in 1 liter. And again, liters will cancel. So we'll multiply that by 1,000. Not too bad making up numbers, I suppose. Will give us, I'll go over here, 2833 milliliters. Maybe we clean it up to 3 sig figs based off of everybody else that's there. So 2830 milliliters of solution is essentially what we would be making. So what that would mean is he would weigh out about 125 grams of sodium chloride, and you would dissolve it in enough water to get to a total volume of 2,833 milliliters. Mix it all together, and you should have a solution that has a molarity of 0.755 molar at that point when everything dissolves in the water. Any questions on that calculation there? Okay. All right. Let's try one more here. How many grams of sodium nitrate is required to make a 2.5 liter of a 0.15 molar sodium nitrate solution? Once again, sodium 2299, nitrogen 14. Sodium nitrate in this case, we obviously have molarity given to us. So in case you were not sure maybe where to start, we do have the molarity. We do have the volume. So again, if you were not sure, the only thing we don't have is moles, which seems like a good place to start. And that's good because ultimately we're looking for grams, and we know how to go from moles to grams, again, using the molar mass from the periodic table. So again, if you just sort of check off what was given to you, probably what's not given to you is what you should start with finding. So to do that, we do want to make sure everybody's in the right units. Our volume is in liters, so that's good. Here, I'm going to turn that into more of a conversion factor version of our molarity, which again, you could use it in either way. So in this case here, we're going to start with our 2.5 liters of sodium nitrate. In this case, we want liters to go away, so we are just going to use it like this, which is basically multiplying it by the molarity. Here, the liters will cancel, and that will get us there 2.5 times 0.15, 0.375, and these are moles of sodium nitrate. So we basically just got to there. So now we do need to go to periodic table there and get our molar mass to use as a conversion factor to basically finish the calculation and take it from moles to grams. So in this case, we have a 2299 for our sodium. We have a 1401 there for our nitrogen. And we do have 3 oxygens, which are 3 times 16 in this case. And that's going to give you, I feel like an 85. Let's see here. Yeah. Mega memory courses are paying off. 85 grams per mole. And once again, we're going to use that as a conversion factor here. So opposites cancel. So we actually do want the moles on the bottom here. And we want the 85 grams up on top. That way the moles will cancel. And that will yield us here. It's like 31.9 grams here of sodium nitrate. Any question on that calculation there? So once again, what that number means is if you weighed out 31.9 grams of sodium nitrate, took enough water, and had a total volume of 2.5 liters, mix it up really good, you should have a solution that has basically this molarity, right? So, question on that there. Or anything we've been talking about, molarity, again, really important unit of concentration, probably the most commonly used unit of concentration for solutions. And again, like I said, you should really, make sure you get rid of the big M, use both units. And secondly, make sure you know how to solve for any of those 3 things, because it's very commonly you need to solve for any of those 3 things that are given to you. Any questions on that? All right, then let's take a look here. What we got next. So we sort of been touching upon this as we've been going through. Again, if we were interested in the molarity of just the ions in each of these cases, so why don't you give it a go here? So we have a 1.2 molar sodium sulfate. So we really want to know what is the concentration of the sodium ion and the sulfate ion in that one. And then we have a 0.75 molar potassium chromate. So we're looking for what is the concentration of each of those ions in those solutions. So take a few moments there and see what you come up with. To these solutions, we were going to make sure we understand how they break apart. So we've actually done this guy a couple of times up to this point. That's probably why we have it's in my head. We have 2 sodiums for every 1 sulfate. And again, that is how it breaks apart. So if you have that solution floating around, for every one of those units you put in there, you got a couple of sodium ions per 1 sulfate ion basically floating around in that solution. So as we talked about, we basically could just do sort of a stoichiometry relationship here. It is a 1-to-2 relationship. So again, here we would multiply the concentration of the whole thing by 2. And for just the sodium ions, it would have a concentration of 2.4 molar. And in the case of the whole thing, to a 1-to-1 relationship, which means if we wanted to know the concentration of just the sulfate there, it would be 1 times the molarity, which would be 1.2 molar. Once again, twice as concentrated in sodium as it is sulfate. As you can see there from my picture, you got twice the amount of sodium floating around for every one of the sulfates. Any questions on that one there? Now, potassium chromate breaks apart into a couple of potassiums and one chromate, which does have a -2 charge, which is why you actually have two of the potassiums there. So in that solution, kind of like the other one there, you basically will have a couple of potassiums floating around for every one of the chromate ions basically floating around in that solution. I think we talked about it last time, but that's pretty much where you find ions. They're in solutions floating around, ready to react, basically, or just kind of floating around doing nothing. So same approach here is a 1-to-2 relationship between the whole thing and the potassium. So we're going to times the whole thing's concentration by 2, and that will get us 1.5 molar for our potassium. It is again, 1-to-1 relationship between the whole thing and just the chromate ion. And that again would mean we would multiply the molarity here by just 1 or keep it the same, which would be 0.75 molar. Any questions on, again, that relationship? Doesn't happen a lot in this class for us, but it can happen. Again, maybe if they're not interested in the whole thing, but just concentration of a certain ion floating around, that again is how you relate it, whole thing to each of the ions. Any questions again on that there? About molarity, we also talked about obviously molarity here of ions. We're going to talk about a very common process that we talked about last time and sort of the calculation that goes with that, which is a lot of times solutions are sort of purchased and what are sometimes referred to as stock solutions, which are really concentrated solutions. And oftentimes when you want to go use them, you do have to do the process known as dilution, where we dilute those sort of really stronger concentrated solutions down to a little bit more manageable of a solution in terms of their molarity. So we do a dilution, and one of the most important things when we do a dilution is the only thing that we add is more solvent. And in a lot of cases, as we've been talking about, a lot of times water is that solvent, but again, doesn't always have to be water. But oftentimes, really the only thing that we're adding is more of the solvent or water. And what that means is the moles of the solute before you do the dilution and after you do the dilution will actually be the same. And the thing that's actually reacting in a solution when you do any type of chemical reaction is actually the solute, the stuff floating around in solution is actually the stuff that does the reaction or goes through a chemical reaction. The solvent doesn't. It's just there to provide really a medium for those ions to float around in the solution. So when we do a dilution and we add more solvent, the moles of that solute stays the same, but the molarity changes. And the molarity changes because, again, the real definition of molarity is moles of solute divided by liters of solution. And as we've talked about, right, solution is the solute plus the solvent, which means when we add more solvent, when we do a dilution, the only thing that changes in this calculation is the number on the bottom gets bigger, right? If the number on the bottom gets bigger, the molarity goes down, right? It gets diluted basically because you have a larger number on the bottom, right? So small number divided by a large number gives you a small number. So when we're doing a dilution, we're really just adding more of this bottom number here. We're making this guy bigger. And the result of that is that the molarity for that solution will actually go down. And that's what it means to be diluted. We have basically more solvent than we started with, and more solvent to solute ratio gets smaller, and the molarity also goes down. So this is a process where you could do a dilution very fancily with a volumetric flask. Volumetric usually means expensive and don't break it, and also means that it has usually just one marking on it. And for example, that would be the marking here for 500 milliliters. And you would start with a little bit of water, perhaps, add your more concentrated solution in, and then top it off with some more water. Give it a mixy, shaky with the lid on and not drop it. And you will now have a lower concentrated solution. You could also, this is also how you can make a solution, just a solution by itself, very accurately by using a volumetric flask. If you had a solid, you put a little bit of water, put a little bit of solid, get the solid to dissolve, and then fill it up to the line here. By the way, if you were doing this and you went above the line, can you just pour out the excess? You could not, because what's in that right now? Your solute, right? So if it was a solid, it would be dissolved, or if it's that little guy that you just diluted, when you would pour it off or you miss the line, which is a very common thing when people use this for the first time, they go, oh, I'm way up here. Can I just pour it off back to the line? You can, but you will also be dumping out your solute, which means you will not have the right molarity that you want. So it's really important when you use something like this, if you should happen to use it, usually what you want to do is kind of fill it to here, use like a wash bottle and just kind of fill it very slowly, and even like a medicine dropper at the very end to make sure that you get it, right at the line, that you don't go over the line or anything like that. All right. So there is a formula that we use for dilutions, and this is the dilution formula. M1V1 equals M2V2. This is before and after the dilution. Typically, these guys over here are the more concentrated solution. This guy over here is on this side are usually the more dilute solution. I personally use M1V1 equals M2V2 because molarity is really the most common unit of concentration. Most books these days, use C1V1 equals C2V2, where C is just a generic unit of concentration. And the reality is, although molarity is really the most commonly used unit of concentration, you technically could go into this equation with any unit of concentration. So you could go in with like percent mass to mass, like we did earlier on both sides, percent mass to volume, percent volume to volume, any type of unit of concentration you could use on both sides. So your book probably goes with the C1V1 equals C2V2, but a lot of people will just call it M1V1 equals M2V2 because molarity is that sort of most common unit of concentration. All right. So why don't we try one here and see what happens? What volume of 19 molar sodium hydroxide must be used to prepare 1 liter of 0.15 molar sodium hydroxide? Okay, so let's take a look and see what we got going on. So basically we have a bottle here, professionally drawn there as a box there. That is 19 molar sodium hydroxide here. We basically want to make another solution over here that has a volume of 1 liter, or I'll go for 1,000 milliliters as well, and has a molarity here of 0.15 molar. So this is a dilution equation. There's nothing really reacting. It's sodium hydroxide. It's just the concentration is changing, right? It goes from 19 molar, which is more concentrated, to 0.15 molar, which is more dilute. So this is our dilution equation. M1V1 equals M2V2. M1 in this case is typically the more concentrated. V1 was not given to us. M2 is given to us, which is 0.15. And V2 is 1 liter in this case, right? And that means that we are going to solve for V1, which means we're going to divide the M1 to the other side. And that would give us here V1 is equal to M2 V2, again, divided by M1. Our molarity here is the same on both sides, so that's good. So we got 0.15 molar times 1 liter divided by 19 molar. Here, the molarities are going to cancel. The units I'm going to be left with when I get my answer is liters in this case. And when you do that, you end up with 0.00789. Or we'll take it to, and that's liters. And I'll move it into milliliters because it's a little less numbers, times it by 1,000 here to convert it into milliliters. Now that number means, what does that number mean? That is how much of what am I taking that from? That is how much I'm taking from the more concentrated guy, right? And I'm going to pop it into my new solution that I'm going to make. which means I would put in here 7.9 milliliters of that more concentrated guy. Would I at this point put in 1,000 milliliters of water? I would not, because if I put 1,000 milliliters of water, I would end up with 1,007.9 milliliters, which is too much volume, right? I want to only end up with 1,000 milliliters or 1 liter is my total volume. So very common dilution question is oftentimes asked, like, how much water should you put in there, right? And we could oftentimes figure out how much water or solvent that we need to put in there by taking V2 minus V1, right? Because V2 is our final solution and V1 is how much of the more concentrated we took. So our V2 in this case is 1,000 milliliters. I'm just going to use the milliliters since I have the other one in milliliters, minus my 7.9. So roughly speaking, I should toss in there about 992.1 milliliters of water to go with there. So I would toss in there 992.1 milliliters of water. That's going to give me a total volume when I mix those two together of 1,000 milliliters or 1 liter. And once again, at that point, if I mix it together, I will then have a solution that has a molarity of 0.15. So typically speaking, when you solve for V1, you're solving for how much of the more concentrated solution you need to use. You're solving for V2, that is usually the volume of your final solution that you're making. And again, M1 would be the concentration of the more concentrated solution, and typically M2 is the less concentrated. Any questions on that? Now, also an important thing with this equation, I'll just back up here maybe. When we use this equation, and if you remember earlier when we were using molarity by itself, and that is moles per liter, which means if we're solving for moles, we want to take liters times molarity, and that is definitely true. So if you're using molarity in a non-dilution type question, you absolutely need to make sure that your volume's in liters, because in most cases, you're going to be wanting moles. But if you are using molarity and volume in a dilution sort of situation with this equation, or the C version of this equation, C1V1 equals C2V2, you can leave the units of volume in milliliters as long as they're on both sides. And the reason it works out, for example, is let's say we were solving for M1, that would be M2V2 divided by V1. And if I just put the units in, molarity, and the top guy was milliliters and the bottom guy was milliliters, they cancel out and I'm back to molarity. So it works out okay in a dilution situation if you want to leave the volume in milliliters, as long as it's a milliliters on both sides. Or if you're solving for a volume, for example, let's say we were solving for V1, that would be M2V2 divided by M1. And if I left the units in milliliters, the difference is here I would end up with milliliters as my answer instead of liters like we did in the previous one. If you don't want to worry about it in this formula, you could just convert it to as well, and you'll have liters and it'll work out fine. But you can use it in this case. The reason you could use it in this case is you can multiply milliliters times molarity, but what you get is not moles, you get what is known as millimoles. So you have to get millimoles. And that's why when you divide millimoles by milliliters, the milli units cancel and you're back to molarity, which is moles per liter. So the reason people always tell you when you're using molarity by itself, you should convert it to liters, is because in most cases you want moles. So if you don't recognize it, if you multiply the milliliters by the molarity, you get millimoles, you're going to be off by a factor of 1,000. So you don't want to do that. So my advice would be definitely 100% of the time, molarity calculation by itself, non-dilution situation, make sure you always have it in liters, the volume, and you'll usually have the right unit that you want. If it's up to you on the dilution, if you want to still convert the volume to liters on both sides, you can. Or if you want to leave it in milliliters, it will work just fine with the molarity. Any questions on that there? All right, so let's take a look at another one here. Let's do this one. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? Okay, so once again, we have a 5 molar calcium nitrate solution sitting there. And we eventually want to make a solution that has a total volume of 500 milliliters and a molarity of 0.25 molar. It is also calcium nitrate, which means all we're doing is a dilution here. So we're going to do a little M1V1 equals M2V2. In this case, truthfully, it really doesn't matter which one you call ones and twos, but again, usually the more concentrated guy ends up on the ones. So for me, I'm going to go M1 is 5 molar. V1 is what we don't have. M2 is 0.25 molar. And V2 is 500 milliliters in this case. So in this case here, we're going to solve for V1, and V1 will equal M2 V2. And again, we're going to divide that to the other side and put it on the bottom, basically, and M1. Going to put our numbers in here. I got 0.25 molar. I got 500 milliliters. Once again, I'm going to leave it in milliliters. That just means when I get my answer, I'm in milliliters. If you want to convert to liters, you would get liters at the end when you would do the calculation here. We're going to divide it by our initial concentration. And again, this is why we could leave it in milliliters, because those guys are just going to cancel out and leave us with milliliters. That's like a 25 maybe, yeah. 25 times 500 divided by a 5, 25 milliliters there. That's 25 milliliters of what? Of the calcium nitrate stronger solution, right? So that, by the way, is not your answer in this case, right? Because we're looking for the amount of water, right? So 25 milliliters when we solve for V1s, how much of the more concentrated we put in there. Now we can figure out our volume of water by taking our final volume, which is 500 milliliters, and subtracting our 25 milliliters we tossed in there. And that's probably a 475 on that there. Yeah. So we would need to put in there 475 milliliters of water with it. That's going to give us our 500 milliliters total volume that we need. And once again, once you give it a little shaky, more of a mixy, you'll get a 0.25 molar solution there of calcium nitrate. Question on that. So it's a very common sort of question that's asked in dilution problems, is more so like how you make it, or how much water would you add or something like that. So make sure you do read those questions carefully, that you're answering what it's really asking. Any questions on dilutions? All right, so we're going to talk about some properties of solutions now, if we get there. And some of the properties here we're going to talk about is a semi-permeable membrane. And a semi-permeable membrane is a membrane that allows certain size molecules to pass through. So, for example, oftentimes you can't see it, but essentially you have a membrane from one side, say, to the next. And that's going to erase everything. So let's try that again. And although you can't really sort of see it per se, there's kind of holes in the membrane. And those holes are going to allow only really certain size molecules to pass through. It's going to restrict them based on size. So, if you got some type of little guy, he's going to have no problem, fitting through the hole. But if you have a little bit bigger of a molecule, he's going to kind of get stuck and not going to be able to basically pass through that hole. So it allows certain size molecules basically to flow from one side to the next. And sometimes we do describe molecules in a couple of different ways. Colloids, these are much larger than solute particles. They are large molecules like proteins, or groups of molecules or ions together. They are homogeneous, just like a homogeneous mixture means they look the same throughout, right? And that's sort of the same idea. Now, colloids do not settle or separate out. They are small enough to pass through filters, like a piece of filter paper that you might use with a funnel. A little filter paper as well, although you can't really see the holes. There's holes in it, right? It allows certain things to go through, like when you make coffee, right? Your water molecules could go through, right? And some of the and it obviously gets some of the coffee going through, keeps all the coffee grains from going through because it's too big. So they can pass through filters, but they're too large to pass through these semi-pyramidal membranes. Our cells, right, have membranes, right? It allows certain things to filter in and filter out through in our body as well. Suspensions, on the other hand, are heterogeneous, non-uniform mixtures, and they are much different than colloids. These are things that you can kind of like see with your naked eye. They're oftentimes trapped by both filters and semi-pyramidal membranes. So, for example, if I had water that had sand in it, yes, I could see the sand in the water, right? That is like a suspension. If I take that sand and water and pour it through a funnel that has filter paper on it, what's going to go through? Water, small enough, right? The sand is going to get trapped on the filter paper, right? So that it would be like a suspension. I think you might use sand in one of the experiments. Maybe it's coal, but I think they use sand these days. So here's a picture of that. On the left there, we have our solution, which is our circles. They're floating around. We have our suspensions, which again, like sand, if you put it in water, right, would settle down to the bottom. You'd be able to see it. And we have our colloids, which are also floating around. You won't be really able to see them. We will be able to filter through on a piece of filter paper. That again is going to trap our suspension, going to let our solution and colloids basically pass through. You also take a membrane like that, which will allow really only our solution molecules. I feel like the next experiment is the one where you put everything in like a dialysis bag and you see what comes in and comes out. And I think you'll do that in the next experiment. You'll basically have a dialysis bag, which is like a membrane. Again, it has holes that allow certain size molecules to pass in and out of the solution. And it's the fun experiment where you wait like 30 minutes and go, what's in the solution? You test for what's in the solution. You wait another 30 minutes and see what came out. You wait 4 hours later and you pop the bag open. Hopefully not 4 hours, but you pop the bag open at some point and see what's still in the bag and stuff like that. So I think you'll do that eventually. Let's talk a little bit about osmosis and dialysis as well. Osmosis is basically the flow of water molecules from one side of, say, a membrane to the other. So, for example, if you had a tube and in between the two sides, you have a membrane here. And on one side, say you had salt water. On the other side, you had just pure water. What happens is the process of osmosis will make the water molecules, which is a lower concentration. The water is a lower concentration because the salt water has salt in the water, right? So stuff dissolved in it. So there's more particles, more concentrated in there. Pure water has nothing in it. And what will happen is by osmosis, all the water molecules, which are small enough to go past the membrane, will go to the other side where the salt water is in an effort to basically dilute down the salt water, basically to try to lower the concentration. It will continue to flow until it hits what is referred to as the osmotic pressure. And the osmotic pressure is basically when atmospheric pressure pushes back down on it, and it prevents the water molecules from continuing to flow. So it kind of pushes back down on it. It won't let any more water molecules go to the other side. That is also what happens when you do something like reverse osmosis, right? Reverse osmosis means that you apply a pressure greater than the atmospheric pressure back down on that. And what that happens is it sends all the water molecules back the other way. If you have a lot of filters here to grab everything you don't want in your water, you have now kind of purified water on this side through the process of reverse osmosis by pushing basically the water molecules back the other way. Now, water has no osmotic pressure, as I mentioned, because frankly, it has nothing dissolved in it. One way that you can figure out or look at osmotic pressure is osmolarity, and that is a unit of sort of concentration that takes pressure into account. our osmotic pressure into account. And you do it by taking I times the molarity, for example. I is basically the number of particles. And osmotic pressure is all based on how much particles are in the solution. So for example, if you had a 2.5 molar solution of sodium chloride, and you had a 2.5 molar solution of calcium chloride, you may think that they both might have the same osmotic pressure. But in the case of sodium chloride, it will break apart into a sodium ion and a chloride ion. And for every one of those guys, we basically get 2 particles, which means the I value here would be 2. When we have calcium chloride and it goes for a swim, you'll get a calcium ion and 2 chloride ions, which is a total of 3 particles in that solution, which means the I value here would be 3. That means if we calculated the osmolarity for our sodium chloride in the above example, it would be 2 times 2.5 molar, which would give us 5 osmolarity for the osmotic pressure of sodium chloride. If we did it for our calcium chloride, we would take 3 times our 2.5 molar. And I know it's a long night, so I'm going to go to the calculator myself. You know, it's been a long night. Don't want to get the wrong number there. 7.5 osmolarity. The one that actually has more osmotic pressure is the calcium chloride because it actually has more particles floating around in the solution. Osmotic pressure is a property of solutions, which is known as a colligative property. And what that fancily means is it's based on how many particles there are in the solution. So the more particles there are in the solution, the greater effect it has on things like osmotic pressure. This is also, for example, why you have more particles in the solution. It affects things like the normal boiling points and, say, freezing points of solutions. So, for example, water normally boils at 100 degrees Celsius, right? And 0 degrees Celsius. And a lot of cars, you put antifreeze into your car. Antifreeze is a solution that has a lot of particles in it. And by having that antifreeze mixed with water when you put it in your car, it will actually elevate the boiling point of water in your car. So it doesn't boil at 100 degrees Celsius in case you're in a really hot environment. Your car won't overboil because of that. Antifreeze is also an interesting thing because it will actually do both things. It will increase the temperature of the water for boiling. It will actually lower the freezing point of water as well in case you live in a really cold place where you got to dig yourself out of snow in the morning. And it will make sure that the fluids in your car there will not freeze because it will lower the freezing point of water in your car. So antifreeze, when we put it in the cars, it actually does both things, and it's based because it has a lot more particles in the water in your car than it would if you just had water by itself, because water by itself, 100 degrees Celsius, you're driving through Arizona, not a good deal, right? Because that's like, you know, every day in July, right? It's 100 and something out there, and that's not going to be really good for your car, right? And stuff like that. So lots of property solutions are based on how many particles are in that solution, and it has effects on a lot of properties of those solutions. Any questions on that? All right, we're almost there to the end, but we're going to lay it up